Okay, we're going to go ahead and review Charles and Gay-Lussac's law for your quiz. So let's start with Charles' law. So in Charles' law, it's important to understand that we have a system, whatever gas we're dealing with, that gas is going to have a constant pressure. So meaning that it's in some kind of container that can expand or become smaller depending on the pressure of the gas. Okay, so an easy example would be a balloon. So let's say we have a balloon here, right? So in this balloon, so if we have, let's say I have a certain amount of gas, which we'll represent with, we'll go 1, 2, 3, 4, 5, 6 particles. If I put this balloon in the freezer, what's going to happen is those particles are going to slow down. So they're going to hit the container less, and the volume of this balloon will go down. We'll still have the same particles in there, but the volume is going to go down. So all Charles' law is saying is that if my temperature decreases, then my volume will decrease. And then the other way around. If I heat this balloon up, it's going to expand and get bigger. Okay, so there's a direct relationship, which is when my volume goes up, when V1 goes up, then my my temperature goes up, my volume will also go up. Okay, so that's the equation for that. So they're directly related. Okay, let's look at, and that's the equation we use. Let's look at Gay-Lussac's law. So this has to do with pressure and temperature. In this system, we have a constant volume. So the volume it's not changing. Okay, so let's say we have some kind of container with gas inside of it, right? And in that gas can't change shape. So let's say we increase the temperature, so we heat this up, right? When we heat it up, particles are going to move quicker, but the volume's not changing. But these particles, they're going to have greater motion, so they're going to have more collisions. So we're going to have more and more collisions. Sorry, this looks like it's more particles. I was trying to draw arrows. There's more and more collisions, right? Because we heated it up. So when my temperature goes up, my pressure is going to go up. Because things can't expand in this situation, so they collide more, so my pressure goes up. So that's all the law is saying. Okay? The opposite is also true. When my temperature goes down, my pressure will also go down. Okay, so we represent this law mathematically as pressure 1 is equal to pressure 2 divided by temperature 1 over temperature 2. Okay? All right, let's look at some practice problems. So the hardest thing about these practice problems is identifying which equation am I using, which problem am I dealing with. So here's the first example. It says, so when you're going through this, make sure you list all the variables, and it'll kind of let you know what you have to do. It says, a sample of neon exerts a pressure of 120 kilopascal. So that's pressure, right? So I know I'm dealing with pressure. So I'm probably not going to do Charles' law because Charles' law is volume and temperature. It says when the temperature is 400 Kelvin, what is the pressure when the temperature is raised to 600 K? So I'm dealing with temperature and I'm dealing with pressure, right? So this would be my T1, this would be my T2, this would be my first pressure. Okay, now let's go ahead and plug all that in. We know we're using this equation here. And I know that this is already in Kelvin, so I don't have to change anything. So I'm going to go 120 divided by my temperature, which is 400, is equal to my P2, which I'm looking for, divided by 600. Okay, easiest way to get rid of a fraction is to cross multiply. So I'm going to cross multiply that. That would give me 120 times 600. Right, 120 times 600, and I'm not worried about units yet, equals P2 times 400. Right, I cross multiplied this and I cross multiplied this. I want to get this by itself, so I divide 400. This cancels. I'm left with that as my answer. Okay, so if I plug that in, that would give me, I would go 120 times 600 divided by 400 would be 180. So my P2 would be 180. 180 what? Well, kilopascals, right? And let's see if that makes sense at the end of the problem. So this thing was heated up. If something's heated up and it can't change shape, then yes, the pressure should go up, so that makes sense. Let's look at this next problem. So it says a sample of gas occupies a volume of 160 milliliters. So I'm dealing with volume here at 91 and temperature at 91 degrees Celsius. What will be the volume? So I'm looking for a new volume of the gas at a temperature when the temperature drops to 0. Okay, so that would be my T2, this would be my T1, this would be my V1. So I'm dealing with volume temperature. Volume temperature, or what am I going to, I'm not doing the last one I did, now I'm doing Charles' law. I'm using this equation, right? Very similar equations, but different variables here. All right, then we just go ahead and plug it in. But we have to change 91 and this to Kelvin. So 91 is going to be 91 plus 273. So 91 plus 273 will give us 364. So it's going to be 160 divided by the temperature, this in Kelvin, 364 equals my new volume, which is what I'm looking for, divided by my temperature, which is 0 plus 273. Well, that's just 273. I cross multiply. So I go 160 times 273 equals V2 times this. Take this to the other side, right, by dividing. So I want to take that to the other side. So I divide by both sides by that. 364. That cancels. And that's my answer. So my answer would be 160 times 273. So 160 times 273 equals, divided by 364, gives me 120. Okay, so my second volume is 120. Well, what's the units? It's 120. We're dealing with milliliters, right? Because we had started with milliliters, so 120 milliliters would be my final answer. Let's see if this makes sense. Well, if I cool the gas down, yes, the volume should get smaller. Just like when you put a balloon in the freezer, it's going to decrease in volume. So that's correct. Okay, so main thing is you got to read the problems, you got to label the variables so you can figure out which equation you're going to use.